Welcome back in the third video of the series about multivariate calculus. Today we are going to compute volume integrals. Last lesson we analyzed double integrals. Now we add one more dimension. A solid region E is said to be of type 1 if it lies between the graphs of two continuous functions of x and y. This region can be defined as E being the point in the 3D plane, such that xy are in the region D, and z is in between the function u1 and u2. As before, we can distinguish between two main types of regions, but for now we restrict our attention only to these scenarios. We have either a type 1 volume with a type 1 projection or same type 1 volume with type 2 projection. Here type 1 volume means, as in the definition that we gave, that it is bounded by functions of x and y, and the projection is the region D. It can be of type 1 or type 2, as we saw in the definitions in the previous videos. If you still have not watched that one, type 1 region D means that it's bounded only by functions of that depend on x, while type 2 region means that it is bounded by functions that only depend on y. Okay, now we can give some definitions. So, if the projection D of the solid region E onto the xy plane is a type 1 plane region, then the triple integral of f is equal to the integral from a to b, then from g1 of x to g2 of x, and then from u1 of xy to u2 of xy of the function. On the similar way, if the projection D is a type 2 plane region, then the integral is similarly the integral from C to D, and then the integral from h1 of y to h2 of y, and then from u1 to u2 of the function. Here we see that the difference is that, of course, here the functions are different. Here they depend on y and there on x. But mainly we have to note that the order of integration is different, since here we integrate towards y first and then towards x, while here we integrate towards x first and then towards y, because here we have functions that depend on x, then y depends on y varies between those bounds, and here we have functions that depend on y, and x varies on those bounds. If we have a different order of integration, we may not reach a finite result of the integral. For example, now we have an exercise. We want to evaluate the triple integral over the region E of the function z, where E is the solid in the first octant bounded by the surface z, given by 12 xy, and the planes y is equal to x and x is equal to 1. We can visualize easily this volume in this way, where D is the projection, and we see it's a type 1 projection, and this is the solid region. We can define this region to be the points in the plane such that x varies between 0 and 1, as we see. Then y varies towards between 0 and x. So we see y varies towards 0 here, and the line now y is equal to x. And z varies between 0 and 12 xy. So z varies towards 0 and this line. Okay. To solve the integral now, we use the formula that we saw. as now we vary towards, we see the bounds that we find for the region E, we apply them and we use them as bounds in our integrals. Accordingly, so these are the bounds for x, these are the bounds for y, and these are the bounds in a way for z. Now go to the next page to solve this integral. So as a first step, we of course evaluate this first integral, and we have the bounds 0 and 12 xy. Then we simply substitute the bounds. Here, for example, we had 12xy squared over 2 minus, of course, 0 squared over 2, and so we obtain this result. Then we can proceed by evaluating the next integral, so the one towards y. In this case, we have that most of the terms don't depend on y, so we can just take them out. And here we just have that, this term gives us y to the power of 3 divided by 3, and the bounds are 0 and x. We evaluate then on the bounds and we multiply by this term, and we obtain this integral that is easily solved in this way. So we take out again terms that don't depend on x, then x to the power of 5 gives us x to the power of 6 divided by 6, and the bounds are again 0 and 1, and just substituting the bounds we get 72 over 18, that is equal to 4. We can visualize this process that we just computed in this way. So we had that z varied from 0 to 12xy, and we keep x and y constant. So we see here z is represented by this arrow that varies from 0 in the xy plane until the function 12xy. Similarly, we have for y that it varies from 0 to x, as shown in the figure, and for x it varies from 0 to 1. The same procedure that we applied for volumes of type 1 can be applied to volumes of type 2 or 3. Simply, type 2 volume means that it's bounded by surfaces that depend on y and z, and type 3 volumes are bounded by surfaces that depend on x and z. Also here we might classify which is the projection D, but the procedure is the same. In some cases, it might be handy to change coordinates. For example, we might have a cylindrical symmetry, and we want to change Cartesian coordinates to cylindrical ones. The conversion is such in this way. So we have that x becomes r cosine theta, y becomes r sine theta, and z stays the same. The dv, that was dx, dy, dz, becomes r, dz, dr, d theta, and we have to be careful not to forget this r. We can summarize what I said in this way, and we can visualize our cylindrical surface in this way, where the angle of theta is the one reported here, and r is simply the radius. Similarly, we can also convert in spherical coordinates. In spherical coordinates, we have that the integral of the function translates having the x that becomes r sine phi cosine theta, y translates in r sine phi sine theta, and z translates in r cosine phi. Then the dv becomes r squared sine phi dr d theta d phi. We have to remember that here we have to add r squared sine phi. We can visualize the spherical coordinates in this way. So the angle so the angle phi is in between the z-axis and the point, but in the vertical plane, let's say, and the angle theta is in the horizontal plane, so between the x-axis and the projection of the point on the xy plane. In physics, or physics or engineering or other books, the angle phi and the theta can be swapped, but usually in mathematics it is kept in this way. In this other drawing, instead we can visualize the infinitesimal volume element. Here in the picture there's a rho, but for us rho was r, and yeah, we can see here the variation on the angle phi, and here the variation the angle theta, and this being r d theta. With this, we conclude our last video on volume integrals. In the next lesson, we will see line integrals, and then we will also look at some theorems that relate a bit some of the concepts in multivariate calculus.